Yeah, a whole bunch of them. Let me actually put this down so you can write on it. It was actually trying to tell us something, and we weren't listening. I wasn't listening last time. Let's learn from this. Notice what the problem we keep having is that this y, when you take that minus sign through, you end up getting a minus y over here is less than y minus u is less than epsilon minus x plus y. So I can cancel it from the right-hand side, but not from the left-hand side. So I actually need to notice something right here. I know that y minus u is bigger than 0. So rather than worrying about this side over here, I should just say 0 is less than y minus u was less than delta because of how I chose to write down I chose u to the left of y. Yeah.
Why is there an x minus u in the left?
Okay. So what we're trying to get at is to be able to get, so this is all wrong. We're trying to get an x minus u. That's what we need. That's our goal. So this is what I know for the case. Let me rewrite this all so it looks pretty. So instead of just the case for this right here, I also need to know that x minus epsilon, I need to know that u is less than y. So that y minus u is less than delta. That's what I need to know. So then when I plug this back in, you're going to have 0 is less than y minus u is less than delta. Plug in for what delta was. And now you have 0 is less than y minus u is less than y minus x minus epsilon, which is equal to y minus x plus epsilon. Now the y's are going to cancel, and you have 0 is less than, minus u is less than minus x plus epsilon. Add your x over, yes.
Okay. That was really simple.
Yeah. Now the trick is that it's not so pretty when you're in the case, here again is our x, here's x minus epsilon, here's x plus epsilon. If we choose y down here, then this was our delta. And so if you go an amount over this way and choose your u to be between y and x. Now life isn't quite so easy when you're actually trying to add them up. Because now you have an x minus u, a u minus y, and then plus your delta to get everything added up. And you end up having 4 cases. I don't want to do 4 cases. There's a much shorter way to do this. So let's do it the shorter way. Let's get us a new page. Okay, so I'm rewriting it. Show that for each y in x minus epsilon to x plus epsilon. This is actually a homework problem in the book. If you want to look at that, I'll tell you which one it is. Yeah. I'm just trying to write it down from memory. Oh, I can write it a little bit easier than this. Let me copy it. This is number 3, page 54. So prove that x minus epsilon to x plus epsilon is a neighborhood of each of its members. In other words, for all y in x minus epsilon to x plus epsilon, there exists a delta greater than 0 such that y minus delta to y plus delta is a subset of x minus epsilon to x plus epsilon. That's what we're trying to prove. So the proof is actually quite a bit shorter. What's our first statement? What's our hypothesis? Yeah, fix epsilon greater than 0 and x in the reals. And then we need to get a y in x minus epsilon to x plus epsilon, right? Now, here's our little scratch area. So here's our y plus epsilon, here's our y minus epsilon. Sorry, I need the x's first. And then, I don't know, we'll make y be right here. So what do you think we should choose? Should we choose this distance or that distance for our delta? The smaller one. So choose delta to be equal to the minimum. Let's try that again. Minimum of y minus x minus epsilon or y minus x plus epsilon. So the smallest distance from y to the endpoints. Okay, so far it's the same. Now we're only going to have 2 cases with this one instead of the 4 cases because we're going to use some absolute values on this one. So case 1, x minus epsilon is less than y is less than or equal to x. In this case, that means y is over on this side. What would delta be equal to then? It'd be this distance right here from here to here, right? So that's going to be equal to y minus x minus epsilon, right? So far it looks similar. Now here's where we're going to change it a little bit. We're going to look at, oh, that didn't go there. Let's look at the absolute value now of x minus u. That's what we care about. We need a u. Let's get our u. Then for each u in y minus delta to y plus delta, it doesn't matter. We're going to have x minus u in absolute value is equal to x minus y plus y minus u. This is adding and subtracting the same amount. It hasn't changed anything. Are we good with that? Okay, triangle inequality. Triangle inequality allows me to split them up. But y minus, I now want to look and see about plugging in for my delta. The y minus u has to be less than delta because delta is inside that neighborhood, right?
Yeah.
Yeah, so that's less than x minus y plus delta. What is delta equal to? Yeah. Now, how am I going to be left with this epsilon? Where do I know y lives? Yeah. So x minus y would be less than epsilon, right? Well, actually, let me not go straight to that because epsilon's a cancel. The absolute value of x minus y is actually just x minus y. It all cancels and you're left with epsilon. Yes. Well, I have a strict inequality right there. So that equal doesn't change anything. So thus x minus u is less than epsilon. Now we're going to go back and look at the second case. We're going to have x is less than or equal to y is less than x plus epsilon. And so in this case, well, we'll just scroll up and look at it. That means y is over here to the right, so delta is going to be x plus epsilon minus y. And for each u in y minus delta to y plus delta, we're going to have y minus u is less than delta. Now we can plug it in. X minus u is equal to x minus y plus y minus u. And that, by the triangle inequality, is less than or equal to x minus y plus y minus u. Replace for the y minus u, that's going to be strictly less than x minus y plus delta. And now tell me about x minus y. If y is bigger than x, then what's the absolute value of x minus y equal to?
Would be,
Y minus x, right? And delta is equal to x plus epsilon minus y.
Actually, cancel.
You're left with epsilon. Thus, x minus u is less than epsilon. Now, our conclusions. In both cases, x minus u is less than epsilon. And so, remember what we're trying to show? Since u in y minus delta to y plus delta was arbitrary, I know that, and u is in x minus epsilon to x plus epsilon, we have y minus delta to y plus delta as a subset, x minus epsilon to x plus epsilon. That's something we feel like we should be able to prove by drawing pictures, which makes it a little bit harder to write up. You get headed down the wrong track with the cases and don't realize you need a zero someplace. Yeah. Does that make sense? That's actually a good proof. There's a reason we took the time to do it. We're actually going to need that a little bit later on when we talk about opening closed sets. We're going to need that methodology. Okay, let's see. Where were we? Do what? Yeah, it needs serious help. I've actually found someone who's willing to bind it, but now I'm not willing to give the book up for enough time for them to bind it. So we'll see what happens.
you just step over.
Christmas break, more than likely.
Step over.
Duct tape.
I don't want you to ruin it.
No,
Yeah,
just,
okay. Listen to reason. Thanksgiving or Christmas break.
Yes, I'm thinking so.
Ignore that.
How long do they say?
what do you mean
I
that?
haven't, I talked to them at the library and they said a couple of days, but I have to go talk to the bookbinders themselves, but typically, because they have to re-glue it and it has to sit until the glue hardens and everything. So, yeah. Yeah, it survived several years in this condition. Just getting slowly worse. Okay, we did that on the board last time. So we had an alternate definition for convergence. What was the original definition? Okay, let's see if we can remember. A
There
sequence,
has to be some arbitrary value that you pick a point, and then every subsequent point is between.
yep, after that. Converges to A, yeah, let's put it into words. Arbitrary value for all epsilon greater than 0, there exists a capital N in the naturals such that for all n greater than or equal to capital N, n minus A is less than epsilon. That's what you were saying.
Or we could say, just say it's bounded, right?
Well, it's where
Isn't
we're
that saying the
headed.
same thing?
Bounded doesn't mean convergent. Convergent means bounded.
But when there's like, when I see some arbitrary value, everything in between.
But remember, this isn't, this value can go to 0, which is forcing them to get closer and closer and closer together. When you say arbitrary, it could be just that value right there. Yes, you have to let it force it to go to 0. So bounded isn't quite the same thing as convergent. Convergent does imply bounded, but bounded doesn't imply convergent. What is the difference between these definitions? Notice to right there, to the if and only if, they're the same. So tell me about what's happening afterwards.
So it's saying that for each neighborhood,
Each
it's going to
neighborhood.
contain everything except a number, like a countable number
Yeah,
of terms.
A
That you can kind of picture it.
neighborhood. A minus epsilon to A plus epsilon. So
The range then?
yeah, here's A. Maybe there's A plus epsilon, there's A minus epsilon. So in here, you have all of your terms of your sequence except a first finite number of them. Now, that first finite number of them does not have to be a small finite number. It could be 10 trillion terms before you get them into that bounded area ever after. So don't let that fool you that finite means 3. Mm-hmm.
Like, there might be a certain number that don't fit into that range
Yep.
until you get to like 1,000.
1,000 or more, and then the rest of them go into it. Yeah. So after some finite, it says it contains all but a finite number of terms. These are first finite terms.
But every term after that. has to be
Yeah.
contained.
Every term after that is contained in it. Yeah. So here's a thought. Oh, the thought skipped us. Have you ever been talking and you had a thought and you wanted to share and you forget it? That happens to me all the time. Can a sequence converge to more than one point? If you guys read this section, which I know you all did, we had a theorem, and the theorem said if it converges to 2 points, they have to be the same.
Yeah, it said that it could symbolically.
Yeah, but in practice, they have to be the same. So
Which-
no, not to more than 1 point. The answer is no. It's just to 1 point, which is a good thing. So let's run through the proof of this one. What's the hypothesis?
Let that sequence converge to and to be. Solution, subsets.
Mm-hmm. So that means that here we're applying convergence. So I get to choose epsilon in this case. When you're proving convergence, you don't get to choose it. But when you're applying it, when you know convergence is given, you get to choose it. So I'm going to choose epsilon to be equal to A plus B over 2. Why would I do that? Suppose here's A, here's B. In the middle is A plus B over 2. So that's going to be my epsilon. This would be A plus epsilon equals to B minus epsilon. Are we good with that? So A plus epsilon is going to be B minus epsilon. That way, then when all the terms are going to A, they can't also be going to B. I can't have the same terms in both areas. Since AN converges to A, there exists an N in the naturals such that for all N greater than or equal to that capital N, I have AN minus A is less than epsilon. Well, that means that minus epsilon is less than AN minus A is less than epsilon. Add A to both sides, and what do we have? But A plus epsilon is equal to B minus epsilon. So for all N in the naturals, N greater than capital N, I know AN is strictly less than B minus epsilon, which means it's not in the interval. Yeah. AN is not in B minus epsilon to B plus epsilon, which is a contradiction. Oh, we probably should have written here converges to A and to B. I'm going to assume that A is less than B. I need that W log without loss of generality. It really doesn't matter which one you choose to be the bigger one and which one you choose to be the smaller one, but one of them's got to be bigger and one of them's got to be smaller. So if this is a contradiction, I have to fix it. A is equal to B. If A is equal to B, then I know that a sequence AN converges to at most one value. There, you can do that. You can do that proof directly. It's a little bit longer because you're going to have. You have to choose an N for converging to A. You choose a second N for converging to B. You take the biggest of the two N's, and then you arrive at terms that are in both sets, close to A and close to B, which gives you A has to be equal to B when you put your absolute values together, because AN and B minus epsilon and A minus epsilon are going to be the same point. A minus epsilon, B minus epsilon, A plus epsilon. Yeah. That one's a little bit cuter of a proof, so I like it a little better. Okay, bounded. This is what Roy was talking about. A sequence is bounded from above if and only if there's a real number m, so that AN is less than or equal to m for all n. The sequence is bounded from below if there's a real number, so that AN is bigger than that number. And then a sequence is just plain bounded if it's bounded from above and from below. So note, this means that a sequence is bounded if and only if there exists a number z such that AN is less than or equal to z for all n. This does not mean that z is the supremum or the infimum. It is just some bound. Let's look at some examples here. Find a value z so that AN is less than or equal to z for each of these cases. So for the case AN equals to 1 over n, what value is going to be our bound? Problem is that 1/2 is bigger than 0. It has to be a bound both upper and lower. So in other words, we want the absolute value of 1 over n less than what for all n? Less than 1. Mm-hmm. You could have chosen 10, 100, a million.
But it doesn't matter.
It doesn't matter. You just have to have some value so that everything, absolute value of it's less than that number. Tell me about 1 plus minus 1 to the n over 2. Well, first of all, before we can figure out a bound, we have to figure out what this looks like. So when n is 1, we have 1 minus 1, which is 0.
It's gonna be between 0. It'll be 0 or 1 each time.
Yeah, alternating. So what should our bound be?
It's always less than
Always less than or equal to 1. 0 doesn't work because, yeah. But 2 would work, a million would work. Mhm.
Why is 0 not work?
Because the 1 value here is not smaller than 0. The absolute value of each term has to be smaller than the number you choose.
So it kind of be like, I mean, I know it's like exactly the same concept, but like these colors, in a way that like, they could be smaller.
Yeah, you can kind of think of it that
So
way.
you're saying that the n can be 1 and it's going to be less than 1, is that what you're saying?
Mhm.
Or you're saying that the less, it can be less than.
No, you have to choose the number here so that no matter what the n is over here, the absolute value of that is going to be less than or equal to 1.
What's the upper bound?
This is just the bound because I did the absolute value of it. The upper bound, I could choose 1 for the upper bound and 0 for the lower bound. Mhm. Tell me about this one.
And to the form, negative 1.
Yeah. Well, except you're dividing by n, so it's negative 1, 1/2, negative 1/3, 1/4. So what is a bound for that one then? 1. Mhm. Now, tell me about this one. This is my own. I just was thinking about it.
Besides this one.
Yeah. You can write that a little bit bigger. So what are some of the first, yeah, these are multiplying together. When, yeah, when n is 1, you have minus 2, right?
Negative 2.
When n is 2, 3/2. When n is 3, it's negative. 1 and 1/3, 4/3. When n is 4, okay, so where are the negative guys going?
Like it's 0.
Not quite to 0. I would submit that for chance they're going to 1.
Oh, yeah.
To negative 1. And where are the positive guys going? Positive 1. So, yeah. And they're bigger than 1. So what is bigger than all the terms in absolute value? 2. But I can't choose anything smaller than 2 because that would eliminate that first term. Does that make sense? Can we do bounded? Maybe? So if AN converges to A, then AN is bounded. That's our next theorem. What's the hypothesis?
Converges.
Yeah, for the
Yeah.
bounded.
Yeah. Then a miracle happens. Yes.
Wouldn't that be nice?
This one is actually,
That's pretty short.
yeah, it's not a long proof at all. I know it converges, so we get to choose epsilon. What number would you like to make epsilon be equal to? Okay, choose epsilon equal to 1. No, it has to be a positive value. Epsilon has to be greater than 0.
We just choose.
Yeah. It doesn't matter which one I choose as long as I choose a positive value. And so, since AN converges, I know that there exists an n in the naturals. Yeah.
I
I guess I just don't really understand why we should, I just want to be honest with like, like, where's that?
Okay, so definition of convergence. It says for all epsilon, there exists an n such that for all n greater than capital N, an minus a is less than epsilon. If I know converges, that's the only thing I have to apply. But I already know it converges, so I'm trying to come up with a bound for it. So when you play with an minus a less than epsilon, that would be minus epsilon is less than an minus a is less than epsilon, add a. Well, then that tells you that minus a minus epsilon is less than a minus epsilon is less than an is less than a plus epsilon if a is positive. Okay, so that's where I'm headed actually. I'm going to choose this a plus epsilon as one of my probable choices for my upper bound. That's why I get to choose a value for epsilon. It doesn't matter what value you choose. Well, we can plug in anything we want as long as it's positive because it says for all epsilon greater than 0. I could have chosen 100. I could have chosen 1/1,000,000th. You know, a teeny tiny number. It doesn't matter what you choose. You just have to choose a positive number because you're applying the definition of epsilon now. I mean, of epsilon. Applying the convergence.
And the number be irrational.
Yeah, it can be irrational. It just can't be negative. Has to be positive, has to be bigger than 0. Yeah. But I chose 1 because it was easiest and you guys suggested it, having read the book and all.
Just say epsilon equal 1.
Yeah, but this, you guys understand the difference. This is not proving convergence. This is applying convergence. Yeah, applying convergence, you get to choose epsilon. Proving convergence, I get to choose it, and I'll never tell you what I choose. It's my secret. It's been my secret for 15 years. When you're proving convergence, I get to choose epsilon. And I haven't told anyone what it is. It's my secret.
Epsilon greater than.
Nope. It's some value bigger than 0. I can choose it as small, as close to 0 as I want. Okay, so fix epsilon equal to 1. And by the definition of convergence, I know that for all n greater than capital N, an minus a is less than epsilon. Okay. By definition of absolute value, I am going to have minus epsilon is less than an minus a is less than epsilon. Add a to both sides. So you have a minus epsilon is less than an is less than a plus epsilon. Oh yeah, these should be 1s. I totally forgot about this. We had been talking epsilon earlier. Good call, Kalai. And now I'm going to take an absolute value. So minus the absolute value of a minus 1 is less than an is less than the absolute value of, well, let me put 1 step in between. Yeah, there were epsilons, they disappeared. Yeah. And so then we're going to have absolute value of a minus 1 is less than a minus 1. It's less than absolute value of a plus 1. Okay, you guys following through that? I stuck in an absolute value so that I could force it to be negative because I don't know if a is negative or positive. But if it's negative, that's smaller than or equal to that value right there. If a was negative to begin with, the absolute value turns it positive, the minus makes it negative, and then this is negative, so those would be the same value, less than or equal to. And if it's positive, then I forced it to be negative. And the same thing is true when I add the absolute value on the other side, it forces it to get bigger. Why do I care? Watch very carefully. That says minus the absolute value of A plus 1, because I'm going to factor it out, is less than AN, is less than the absolute value of A plus 1. I have the same thing on each side except one is negative and one is positive. So AN is less than the absolute value of A plus 1 in absolute value. This is for all n greater than or equal to capital N. So the last infinite number of terms all satisfy this. Now the only thing I have to worry about is the first finite number of terms. So I'm going to choose M to be the maximum of the set A1 in absolute value, A2 in absolute value, up to A sub n minus 1.
Yeah, by minimum.
No, because I took the absolute value of it. So bounded, I just have to say the absolute value of each term is less than some number, not bounded above or bounded below. And then I put in the value that I have above. So I know no matter what that each of these first finite terms is less than or equal to m, because m is the maximum of those. And the last infinite ones is going to be less than the a plus 1. So they're all covered here. By definition of m, I know that a sub n is less than or equal to m for all n greater than or equal to 1. I'll actually just put in the naturals. Thus, an is bounded. And that is done. So convergence implies bounded. Does bounded imply convergent?
Yes, ma'am.
Yeah, no it doesn't.
Yes, not.
Guess not.
No.
Bounded does not imply convergent. So I went to the next screen. Convergent implies bounded.
There's divergence.
Yeah,
That's why I just picked, it's not picked.
yeah.
Lots of convergence, divergence.
Dustin, I love how
Bounded.
you remember calculus. I like try to forget every time.
I try not to do calculus because I love calculus.
Tell me about this sequence right here, minus 1 to the n. What are the terms of this sequence? This thing looks to be bounded. What is it bounded by? Well, in fact, the absolute value is less than or equal to 1. So it's bounded. Is it convergent? We call it divergent when it doesn't converge. Even though it doesn't go to infinity. Yeah, it has to go to one value and only one value.
So basically the increasing or decreasing until it gets
Mm-hmm. Yeah, this one keeps oscillating so it doesn't converge.
I mean, it wouldn't be convergent.
The sine wave, you have to be careful because you're talking function instead of sequence. So they're apples and oranges. The comparison to functions is continuous. And the sine wave function is continuous. Sine of x is a continuous function. But if you do sine of some points, and they're just arbitrary points like sine of the integers, that diverges because it doesn't ever converge to a single value. It bounces around all the time. It doesn't ever go to a single value.
So, converging in others for specific things.
For sequences, for points. we'll talk about continuous.
But yeah, because you said that, for these sequences, we don't even care about that.
Yeah, we don't care about the x values because we know what they are. And so, yeah, these are points. But
See, I always forget that because I always see like,
yeah, it doesn't look like there's any x values on it, but yeah, there are. So this would be the same thing as 1, -1, 1, 1. Sorry, 2, 1, 3, -1, 4, 1. Keeps on going. Yeah.
I remember we're not liking sequences of series until we got the Taylor series.
And then you liked those.
And now I'm like,
Oh, most people don't like those.
That,
Look at me.
it didn't make sense. It did not make sense to me until Taylor McLaurin series. And that really made sense. My professor said, well, if you understand that, you can understand the rest of it.
Pretty much.
I found it only have.
I hope you get to
one
teach
on my-
calculus when you grow up.
I
Take
found
all the
calculus
jobs
have
from the rest of us.
only
I don't know.
in one of my university.
No, there is an intro.
Those are
Oh, I
fun.
missed the girl.
Okay, so let's look at this next example. You actually have seen this one.
I know.
I think I have.
This is, I'm going to show you a reordering of this to show you that it's unbounded. First of all, A1 is equal to 1. A2 is 1 plus 1/2. A3 is 1 plus 1/2 plus 1/3. And let's see, I'm going to look at powers of A2 to the n. That's the trick. A2 to the n, this is going to be 1 plus 1/2, and I'm going to group it together as 1/3 plus 1/4 plus, and then the next 4 terms together. And then it would be the next 8 terms together. Yes. Yeah, and then where does this go? It's going to be 1 over 2 to the n minus 1 plus 1 plus 1 over, well, I'm not going to do all the middle parts. 1 over 2 to the n. Okay, now why would I do that? Tell me about 1/3 plus 1/4. I would submit to you, well, don't add them together. Let's make that be 1/4 plus 1/4, right? It's bigger than 1/4 plus 1/4. Tell me about this next one. This one would all be bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. And the next one would all be bigger than, and there's 8 of them, right? And then the last one would be 1 over 2 to the n. And the question is, how many terms are in that one? The first one had 2 terms. The next one has 2 squared. This one's 2 cubed. So this is equal to 1 plus 1/2 plus 1/2 squared plus 1/2 cubed, except it's 2 over 1/2 squared plus 4 over 1/2 cubed plus 16 over 2. Am I off? Oh, 8, yes, IMO.
That become all the ways half. All of them,
2 to the 4th. Yeah,
all half.
and this is going to be 2 to the n minus 1 over 2 to the n. But then what is that equal to?
All half.
Whoa.
Yeah. So how many terms do you have? You have, if you had 3, you'd have 1, 2, 3 for the cubed. So if you have, you're going to have, yeah. So that tells you that a2 to the n is bigger than 1 plus n over 2. What is the limit of that? Infinity. Is this a bounded sequence?
No,
No.
they will talk. Unless for some reason people.
Therein is another reason why the harmonic series diverges. That was the harmonic series because it was a sum of 1 over n that we started with. Do you guys notice that?
Uh-huh.
Yeah, that's a harmonic. So that's why your harmonic series diverges. I actually showed you that with an integral test. This one's actually easier than an integral test.
Oh, I remember the.
Wasn't there what, huh?
Like a particular series.
Yeah, we did integrals of series. Yes, we did. We did derivatives of series too, yes. I actually like doing integrals and derivatives of series.
That was fun, I remember.
It was.
For me, it's like all information that gets put into my brain in college, like during break, it just like
Falls away. Actually, what happens is you take the next class and it pushes all the old information out.
Exactly.
It does.
My brain does not have enough capacity to comprehend everything.
Sometime we'll get to heaven and we'll get to turn on the other 90% of our brain.
My brain will be like,
Is that true enough? Is that for both sides? Like,
I have no idea.
50% of you
Yeah, I have no idea.
don't.
They use
Why
100.
why do they,
I think
why do
when
they
we
stop
get to heaven,
calculus at calculus 3? Why don't you just, keep on going?
Well, this is the next step in it. You are going on.
Like calculus 4.
You have differential equations. Yeah. Okay, let's finish off with our definition here. We're almost done. It says a sequence AN is said to be convergent if and only if there's a real number A such that AN converges to A. If AN is not convergent, then it is said to be divergent. Divergent does not necessarily mean it goes to infinity. It could go to multiple limits, but it can't converge to a single value. So you could have AN goes to infinity. You could have AN goes to minus infinity. You could have AN goes to 2 values.
You do have an example where it's what it's.
I did an example.
when it oscillates one.
Oh.
Yeah.
Oh, I see. That makes sense.
Or when it jumps between 1 and minus 1. So this one is converging down to 1 and up to minus 1. Yep. So those are divergent. Okay. Give examples of divergent sequences that satisfy the following. The sequence is unbounded.
Or
We
the
did.
harmonic series.
Just put a 1 down diverges.
You just did one.
We just did one.
There you go.
That was the one we just did. How about another one? Surely there are some easier ones than that.
Is that the same thing as like I haven't goes to infinity?
This is the same thing as 1 plus 1/2 plus 1/3.
No, I mean like, you know how when you write the sequence thing, it'll show.
Oh,
And
yeah, I'm giving you the formula. You can write it this way if you want, but when I'm writing the formula, I usually just leave the little superscript off. No, it's not absolutely necessary. It's poor convention to leave it off, but many mathematicians do. Sorry. What's another unbounded one? We'll call it B sub n. Square root of n? Sure. The easiest one. We were getting there. You guys started with the hard and went to the easy. That's fine. On to the next one. Give a case of a divergent sequence which is bounded. We don't want it to converge. We just want it bounded but divergent.
So that's like the negative one.
Yeah. Mhm. That one works. Or sine n, that would be bounded. Or cosine n, yeah. Any one of those would work.
Not tangent.
Tangent diverges because it goes up. Although if you were just doing n's, it shifts over, but it's an irrational number, so the n would migrate through the interval. Yeah, it would be a pain. We won't go with tangent. So, what breaks in the definition of convergence? In the unbounded case, if you were trying to show that Cn converges, say, where would that fail? Yeah, you can't even write Cn minus infinity. You can't write that. You can't write that. So you don't have a limit. Now, look in the second one. So suppose we're looking at this minus 1 to the n. And suppose we thought the limit was 1. Then we're looking at the case where we're going to have d sub n minus 1, and we want that to be less than epsilon. And if you plug in your d sub n, now what's going to happen? You're going to fail here. Yeah. It's only true for part of them. So if you're doing a proof and you can't make it work for all the n, then check and see if it actually converges. It might go to 2 different limits, in which case it's not convergent. Epsilon has to be greater than 0, and epsilon's my secret. So whatever you choose for epsilon, I'm going to choose like much smaller than that to make it fail. Yeah. It's my secret.
Why you can't choose a fixed epsilon.
That's right. Because you have an infinite number of them to check. That's exactly right. Yep, that's why. Okay, we are done. We have 10 minutes left in class. If you want to start looking at the homework, you may. If you want to leave, you may. We are one class period behind, and we're just going to remain one class period behind the rest of the semester. So I reposted the due dates on eClass, but I haven't changed it on the homework and outline dates yet. I will do that eventually. Yeah. Wednesday night. Yeah.
And the outline due the morning.
1.2 is due Wednesday at 3. Yeah, before class, 3:30. Yeah, I guess class starts at 3:30. Probably a good thing. Yeah, let me stop this recorder.
But it said